Hello and welcome to CMG's webinar on Advances in CO2-EOR Reservoir Modeling. My name is Anjani Kumar. I'm the Vice President of Engineering Solutions and Marketing at CMG. I'm pleased to introduce Hussein Nourizieh, a Senior Reservoir Simulation Engineer at CMG, who will be presenting today's webinar. Hussein holds a PhD and a master's degree in petroleum engineering from the University of Calgary. Hussein is the domain expert in reservoir fluid phase behavior and simulation of thermal and solvent hybrid-based in situ recovery processes. Over the past few years at CMG, Hussein has been involved in improving numerical performance of highly complex simulation models. At this time, I'd like to inform you that there will be a question and answer session at the end of the presentation. However, you may submit your questions at any time using the chat window on your screen. Over to you, Hussein.
Thank you, Anjani, for the introduction. Hello, everyone. Today I'm going to talk about advances in carbon dioxide EOR reservoir modeling. In this webinar, I start with a brief introduction to EOR processes. Then I talk about the design steps of the CO2-EOR and the mechanism important to the process. Also, I will talk about the advances in hybrid EOR processes as well as the practical modeling workflow to replicate the field results. We have also some case studies and the conclusions for this webinar. Why enhance oil recovery processes? The oil recoveries from primary and secondary recovery phases are generally in the range of 20 to 40% of original oil in place. Therefore, we have a huge amount of the oil remaining in the reservoir. So the techniques that we apply to produce this remaining oil is called as enhanced oil recovery processes. So here you will see two examples that we are producing the remaining oil in the reservoir with the tertiary or EOR techniques. There are different EOR methods like hydrocarbon miscible injection, nitrogen and flue gas injection, surfactant or polymer injection, alkaline flooding, fire flood, and steam drive. These methods can be applied to specific reservoirs with specific fluid properties. The carbon dioxide flooding as a proven technology has gained a lot of attention in the recent years, and it's due to two major advantages: the additional oil recovery by injection of carbon dioxide, and also the potential to storage carbon dioxide in order to reduce the emission of greenhouse gases. The carbon dioxide EOR can be in miscible or immiscible modes, and it has been proven to be technically feasible in two modes. The carbon dioxide EOR miscible process is preferred because it does have higher recovery compared to the immiscible mode. Because of that, among 123 carbon dioxide EOR projects in the US, about 114 are miscible processes. Even the non-miscible carbon dioxide EOR process is still attractive because of the oil viscosity reduction and the oil swelling by the dissolution of the carbon dioxide. Not all the reservoirs are suitable for the carbon dioxide EOR process. Based on a simple screening, so the reservoirs with the oil with the light to ultra light oils and the viscosity is less than 3 centipoise are the reservoirs suitable for the carbon dioxide injection. So this plot is showing the general approach for the application of the carbon dioxide EOR process. It does have many stages. The first step is data management and analysis. The reservoir development plan depends on the ability to collect and analyze the available data. The data such as reserves, petrophysical properties, and oil price. The second step is screening. Effective screening practices must be employed to identify the best available candidates. So how much oil can be produced and what techniques should be applied. The third step is experimental studies. The lab studies should be conducted to evaluate the performance of the selected EOR method. So the studies such as full PVT experiments, flood test on the representative cores to identify the recovery mechanism involved in the process. Step number 4 is detailed studies. The reservoir simulation is a must for planning full pilot and field project. In this stage, all the design parameters such as well pattern, type of the injection are highlighted. Then the optimum recovery and required facilities such as pipeline are identified. Step number 5 is project feasibility. In this stage, all the potential risks such as environmental and technical as well as the commercial and political factors are evaluated. So in order to evaluate or ensure the efficiency of the EOR method in the field pilot designed and conducted. The results from the field pilot is very useful for fine-tuning the reservoir simulation model. And finally, the optimization with the reservoir model is done at the full field level. As you can see here, the reservoir modeling and the simulation studies are the main steps in the design of carbon dioxide EOR methods or projects. Now the question is, what does reservoir modeling aim at? The main idea is to get a better understanding of the reservoir performance. In order to have a good understanding of the reservoir performance, you should have a representative model or representative reservoir model. So here you will see the steps to make such a model. Step number 1 is having reliable data input, the reservoir parameters, PVT, and some other information from the reservoir. Then you need to do the history matching. The history matching of the production and pressure history data to calibrate the reservoir model. If you don't have any data from field, then you need to run sensitivity studies and optimization. The last step is doing forecast, running different scenarios, finding the optimum design for the project. And also at this step, you can update the model based on the new data from the field. So among these 3 steps, step number 1 is the most important step because it needs understanding of the physics and important mechanism involved in the process. So, and also in order to capture this mechanism, we need to have a reliable and capable modeling tool. So the carbon dioxide EOR processes or carbon dioxide EOR is a complex process, and there are so many different mechanisms involved in this technique. So when the carbon dioxide is injected into the reservoir, it dissolves into the oil, and at the same time it can partition into the water phase. Under a specific temperature and pressure or composition, we may have asphalty precipitation or the reactions in the aqueous phase. As I mentioned before, we have so many different mechanisms involved in these processes, but the most important ones are listed here. The PVT, solubility and swelling, miscibility mechanism, asphalting deposition, wettability alteration, hysteresis, IFD effects, diffusion and dispersion. These are the main mechanisms happening in the carbon dioxide EOR processes. There are also some other process mechanisms, such as matrix dissolution from carbon dioxide injection, aqueous chemical equilibrium reactions, ion exchange, mineralization, that is the dissolution and precipitation of the minerals, and also the effect of temperature on the above mentioned mechanism. In some cases, we may have the carbon dioxide leakage from the or through the cap rock. So in order to capture all of these mechanisms in the reservoir model, we should have a capable and reliable modeling tool.
At this time, I like to ask the audience their opinion about what they think is which of the following complex mechanisms are important and should be incorporated into a reservoir simulation model. And you'll get an option, 4 or 5 options on the screen, and the options are geochemistry, geomechanics, solid or asphaltene deposition, all of the above or none of the above. And you can see here, I'm seeing some of the responses that are coming in. We'll just give a few minutes here. The preliminary results are showing that 13% of the attendees feel that geochemistry is important. 25% say geomechanics is important, and 52% believe all of the above. And it's a very, very subjective question because it depends on your reservoir. Some of these mechanisms may be very important in some reservoirs, some may not be that important. So depending on the reservoir you're trying to model, the simulation model can be developed including some of these mechanisms or all of these mechanisms into a single simulation model. And you can do relative sensitivities on the relative impact of each of these mechanisms on the overall result of your simulation process or the recovery process. Back to you, Hussein.
So as I mentioned, so we need to have a modeling tool to capture all of these mechanisms. So in CMG package, we have GEM, that is an advanced general equation of a state compositional simulator. This simulator can be used to simulate the compositional variation in the reservoir fluid during the primary and enhanced oil recovery processes. Also, we have WinProp package that can be used to generate a PVT model based on labbing the experimental, based on matching the lab experimental data. So GEM simulator can be used for modeling of different processes in various reservoirs. So here you will see a list of the processes or reservoirs that we can use GEM to model them. So GEM can be used for modeling of gas condensate, tight and shale gas, carbon dioxide EOR, WAG, chemical EOR, carbon dioxide sequestration, low salinity water flooding, polymer flooding, ASP flooding, and so many other processes. In recent years, the carbon dioxide flooding is becoming popular in the unconventional and tight reservoirs. We also have the Cmos, that is a powerful tool to run sensitivity studies, history matching, optimization, and uncertainty assessment. So with these studies, we can improve the net present value for the project, we can improve the recovery from the reservoir, and also we can quantify the uncertainties and the risk involved in any project. So before using these tools for any reservoir modeling purpose, you need to understand what is each mechanism in the carbon dioxide EOR processes and how you can capture them in the simulators. So the PVT is the main part of any reservoir model. So in WinProp, you can characterize the reservoir fluid based on the compositional analysis. You will define the components, you can lump them, and you can come up with the minimum number of components for the reservoir fluid. Then you take this model and you will tune the equation of a state to match the lab data. So the lab data such as CCE, differential liberation, separator test, and swelling results can be matched within WinProp. And finally, the tuned equation of a state is used to predict the effect of pressure, temperature, and composition variation on the reservoir fluid properties. When the carbon dioxide is injected into the reservoir, so the gas may not be miscible initially at the reservoir condition. But by multiple contacting of the gas with the oil, the miscibility is achieved during the displacement. There are several mechanisms involved in the multi-contact miscibility that is called as vaporizing, condensing, or combined vaporizing and condensing. The MMP and MME determination is essential for multi-contact miscibility condition. In WinProp, we have different methods such as cell-to-cell simulation, multiple mixing cell, or semi-analytical methods to calculate the MMP and MME for any gas and oil mixture. Also, you can evaluate how the addition of the carbon dioxide into the oil can change the reservoir fluid properties, and what is the mechanism involved by the injection of the carbon dioxide into the reservoir, and what is the mechanism for the miscibility or reaching the miscibility condition at the specified temperature. Also, you can evaluate how the composition of the oil and gas is changing during the multiple contact of the oil with the gas. When carbon dioxide is dissolving into the oil and swelling the oil phase, it can also partition into the water phase. In order to model the solubility of the gas in the water phase, we are using the Henry's model. So in GEM and WinProp, you have the option to directly input the Henry's constant parameter that you already matched with the experimental data into the reservoir model. Or you have the options to use the correlations such as Harvey or Linnaeus methods to model the solubility of the carbon dioxide in the water phase. Also, you can account for the effect of salinity on the solubility of the gases in the aqueous phase. In the right-hand side, you will see how the Harvey's method is well predicting the solubility of the carbon dioxide in the aqueous phase. There is another mechanism involved in the carbon dioxide EOR processes that is called as asphalty precipitation. So in the reservoir fluid, there is a heavy fraction that is called as asphaltene. This fraction is quite stable in the oil, but due to the change in pressure, temperature, or composition, this fraction can be separated from the oil. That is called as precipitation. So in WinProp, you can model the precipitation or the redissolution of the asphaltene by change in the pressure, temperature, or composition. If you have any data, then you can match it in WinProp and you can develop a PVT model to predict the effect of, for example, different parameters such as pressure and temperature on the asphaltene precipitation yield. When the asphaltene is separated from the oil, there are some other mechanisms related to the deposition of the asphaltene in the porous media. So these mechanisms are flocculation and deposition that is happening in the porous media. In GEM, we can capture the deposition mechanism, the flocculation and deposition. So the flocculation is the aggregation of the asphaltene particles into larger particles. So in GEM also you can model the transport of the aggregated asphaltene as suspended components. Also you can model the mechanism involved in the deposition. These mechanisms are surface deposition, plugging, and re-entrainment. In fact, in GEM you can capture the non-equilibrium blockage due to the mechanism involved in the deposition process. When the asphaltene or any solid phase is deposited in the reservoir, then the permeability of the reservoir is affected. In GEM, we have different models such as power law, Kozeny-Karman, and solid absorption model to capture the permeability reduction by the deposition of the solid. So these models are well representing the core flow test results as well as the field behavior. So the way that this model is working is that the permeability is changed by a resistance factor. So in order to change or adjust the phase transmissibilities in the reservoir model. In some EOR processes or carbon dioxide EOR processes, the wettability of the reservoir can be changed. The wettability alteration can be due to asphaltene adsorption or geochemical interaction and ion exchange happening in the reservoir. In the right-hand side, you will see when the asphaltene is separated from the oil, it just absorbed in the surface of the rock. So because of these effects, the permeability of the reservoir can be, the permeability and wettability of the reservoir can be affected. In GEM, we have the options to change the capillary pressure and relative permeability curves as a function of a component composition. In this way, we can capture the wettability alteration from the oil wet into the water wet, or from the water wet into the oil wet. The interfacial tension between injected carbon dioxide and reservoir fluid is really important in the carbon dioxide EOR techniques. So when the process is immiscible, we have a high interfacial tension between the gas and oil phases. So therefore, we should use typical relative permeability curves to capture the rock and fluid interactions. When the process or when the miscibility is achieving the reservoir, the straight line relative permeability curves should be used because we have lower interfacial tension between the gas and oil phases. In GEM, we have an option to change the relative permeability curves as a function of interfacial tension. So when the process is immiscible, we are using the typical relative permeability curves, and then we are switching the relative permeability curves into the straight line relative permeabilities when we have miscibility condition in the reservoir. There is another mechanism for the gas injection processes that is called as hysteresis. In the right-hand side, you will see a non-wetting phase is displacing the wetting phase in the pores. This process is called as drainage. Sometimes the displaced fluid moves back into the pores and displacing the non-wetting phase. This process is called as imbibition process. During the imbibition, some gases may remain in the pores. That is called as gas trapping. If there is no effect of trapping in the reservoir, the same relative permeability curves used for the drainage and imbibition processes. But if we have the gas trapping effect, then a shift in the relative permeability curve should be accounted for the trapping. In fact, the relative permeability for the imbibition curve is different than the relative permeability for the drainage. And it will account for the gas trapping due to hysteresis. In GEM, we have the three-phase hysteresis that accounts for the hysteresis of the liquid and gas phases. The molecular diffusion has shown to be one of the main recovery mechanisms in the fractured reservoirs. The diffusion is the result of the concentration gradient, and the dispersion is due to the velocity variations. In GEM, we have the option to directly define the diffusion for each component in different phases. And also, you can define the dispersivity for each phases. At low velocity condition, the process is controlled with the diffusion, while at the high velocity condition, the process or the physical dispersion is controlled with the convective dispersion. The coupling of the reservoir flow and geomechanics simulation is important for the compositional fluid flow processes such as WAG and carbon dioxide storage. The intention is to study or understand the effect of stress and deformation due to the change in reservoir flow and the fluid phase behavior. The coupling has gained a lot of attention in the recent years to study the effect of compaction, subsidence, formation plugging, induced fracturing, and cap rock leakage, and any other aspects in the stress-sensitive reservoirs. For example, for a safe carbon dioxide storage in saline aquifer, we need the evaluation of the cap rock integrity to stress responses in such a way that we can prevent the leakage happening in the reservoir. So in GEM, we have different constitutive models to study the effect of stress and deformation on the rock behavior. So these models can be applied for the risk assessment in the carbon dioxide sequestration, the deformation of the geological structure due to the fluid injection and production, and also for the geomechanical effects on the coal seams. So here you will see an example for the effect of geomechanics. So in this case, the carbon dioxide is injected into the aquifer, and due to the change in the stress in the reservoir, there is a leakage from the aquifer into the cap rock. So in GEM, you can see or you can evaluate what is the rate of the leakage and how much carbon dioxide is leaking into the cap rock or overburdens. So the mechanism that I talked about them were the main mechanism in carbon dioxide EOR processes. There are some new advancements in the EOR techniques. So because of the differences in the viscosity and density of the injected carbon dioxide and the reservoir fluid, the miscible floods often suffers from the mobility or poor mobilities. So in recent years, the next generation carbon dioxide EOR technology and the advances in hybrid EOR processes could potentially increase the oil recovery from the reservoir compared to the conventional methods. The combination of the carbon dioxide and low salinity water injection or foam-assisted carbon dioxide vac processes are a few examples of these advancements. So the low salinity water injection is a process in which the salinity of the injected fluid is adjusted in order to achieve higher recovery from the reservoir. This process is attractive because it's operationally identical to the conventional water flooding. There is no requirement for the expensive chemicals, and also there is a possible increment in the oil recovery. So the low salinity water injection works well in the oil wet reservoirs with the clays. And due to the ion exchange and the chemical reactions in the aqueous phase, the wettability in these reservoirs can change from the oil wet into the water wet. So therefore, the main mechanism for the low salinity water injection is wettability alteration. So recently, the combination of the carbon dioxide injection with the low salinity water injection could result in higher oil recovery from the reservoir. So in the carbon dioxide vac processes, we have the carbon dioxide miscibility to achieve a good displacement efficiency in the reservoir. In order to control the mobility of the gas, we are using the vac type of injection. So in this process, we have a high recovery factor compared to the gas injection or conventional water flooding. But the main issue is delayed production. In the low salinity water injection, we can take the advantage of the wettability alteration to have higher recovery compared to the conventional water flooding. As I mentioned before, in this process, we have lower chemical cost, less environmental impact, and ease of field implementation. But the issue with the low salinity water injection is lower recovery compared to the miscible floods. If you combine the carbon dioxide with the low salinity water injection, you can promote the synergy of mechanism. So we have the carbon dioxide miscibility in one side to improve the efficiency or displacement efficiency. We are using the vac type of the process to control the mobility of the gas, and also we are taking the advantage of the wettability alteration due to the geochemical reactions with the injected carbon dioxide, ion exchange, and the dissolution of the carbonated minerals. In this way, you can get higher recovery compared to the conventional water flooding, low salinity water flooding, conventional carbon dioxide vac processes, and pure carbon dioxide injection. And also there is no challenge of late production in the carbon dioxide low salinity vac process. So in the top you will see a case that different methods are compared in terms of oil recovery. So as you can see, the low salinity water injection has higher recovery compared to the conventional water flooding. And the carbon dioxide low salinity vac process does have higher recovery compared to the other mechanisms, such as conventional carbon dioxide vac processes, low salinity water injection, or conventional water floodings. In GEM, we can capture all the mechanisms involved in the carbon dioxide low salinity vac processes. We have equation of state compositional simulator that can capture all the miscibility mechanism involved in the carbon dioxide injection. And also we have full geochemistry model to simulate the aqueous reactions, ion exchange equilibria, and the mineral dissolution and precipitation reactions occurring during the low salinity water injection. In order to capture the wettability change, we have the option to interpolate the relative permeability curves based on the ion exchange. In the case that the injected fluid does have different temperature than the reservoir fluid, also in GEM you can capture the effect of temperature on the low salinity water injection. There is another process that recently gained a lot of attention is foam-assisted carbon dioxide EOR. In the gas flooding, we have the issues with the gravity segregation and gas fingering. The injection of the water with the gas is suggested to improve the displacement efficiency or sweep efficiency in the gas flooding. But still, there are some issues with the gravity segregation and gas fingering in the vac processes. By adding foam into the vac process, you can improve the sweep efficiency in the vac. In fact, the foam is used to change the mobility of the gas in the reservoir and improve the sweep efficiency. In the cases that we have a well drilled near the gas oil contact, you can apply foam around the perforations to reduce the gas mobility and production in the wells. In GEM, we have an empirical model to capture all the mechanisms involved in the foam injection processes. This model is working based on the modification of the relative permeabilities. So the relative permeabilities can be modified based on a parameter that is called as interpoolant, and this parameter depends on different properties, such as foam mobility, surfactant concentration, oil saturation, capillary number, oil composition, salinity, and foam dry out. With these parameters, you can easily capture all the mechanisms involved in the foam injection processes. Now that you have a good understanding about all the mechanisms involved in the carbon dioxide EOR processes, you need to know what is the practical modeling workflow to replicate the field behaviors.
Thank you, Hussein. At this time, I'd like to ask another question to the audience. The question is, have you seen improved NPV for an asset after using Cmos to optimize an EOR implementation scheme? The options are yes, no, I have not tried this before. So the results are coming up. You can give a few seconds as well for everybody to respond. Around 22% attendees have responded yes, 9% said no, and 70% have not tried this have tried Cmos to do optimization of their EOR processes. Just for the people, that's good to see that around 21% say that they have tried this and benefited from Cmos optimization. For the people who have not tried this, Cmos is our sensitivity analysis, history matching, optimization, and uncertainty analysis tool that has proven quite useful in optimizing any kind of EOR processes and trying to design the process effectively. Hussein is going to show some of the case studies which show or demonstrates the power of Cmos to optimize these recovery mechanisms. You'll also find several technical papers written by CMG and by different companies in the SP literature that demonstrates how Cmos can be used for improving and optimizing the design of an EOR scheme. Back to you, Hussein.
So as I mentioned, you need to know what is the practical modeling workflow to replicate the field behavior. So here you will see the workflow. The first step is to create a PVT model based on the lab data, such as CCE differential libration. Then you need to use this PVT model in GEM to match the slim tube test results or the core flood test results. So when you are matching the core flood test results, you can come up with some unknown parameters for the reservoir, such as relative permeability curves. The third step is geological modeling. In this step, you will distribute the properties such as porosity, permeability, and clays in the reservoir. Then you are taking the PVT models and the geology and the geological model into the GEM to make the base case reservoir simulation model. In this model, you will capture all the mechanisms involved in the process. Then you will run sensitivity studies and history matching to match any available production and pressure data from the field. So after that, then you will run optimization to find what is the optimum design, for example, for any processes in the field. This is the practical workflow. So right now I'm going to show you some case studies. We have two case studies. Case number one is field scale inverted 5-spot pattern model that shows the application of the modeling workflow. The second case is a field scale model that we have primary and secondary recovery production data, and we want to use this data to tune the reservoir model and then use the model for the WAG optimization. Also in this case, I show you the evaluation of some mechanism for the WAG processes. So case number one is for your reference, and it's showing a step-by-step procedure to make a reservoir model. So for this case, what I did was to match or create a PVT model based on the available data or lab data for the reservoir fluid. So I had the data for CC, differential libration, and separator data, and I created a fluid model in which that I could match all of the data. Then I used the same PVT model and along with the experimental data for the carbon dioxide and oil interactions. I had swelling test results and the saturation or the saturated viscosities and densities by the dissolution of the carbon dioxide into the oil. Again, I used this data in WinPerab to match the first contact miscibility and also the oil and carbon dioxide interactions. In the next step, so because of the slim tube MMP measurements, so I used the WinPerab thermodynamic models to predict the MMP for the injected carbon dioxide and the reservoir fluid. At the same time, I used GEM to make a 1D model and to predict the oil recovery by the injection of the carbon dioxide at the specified minimum miscibility pressure. So again, all the data for the displacement mechanism is matched at this step. Sometimes you have the core flood tests. For this case, I had the core flood test for the WAG process. So what I did, I created a 1D model in GEM and I simulate the WAG processes in the core flood test. Then I use Cmos to run the sensitivity study and history matching to match the core flood test results. And I came up with the relative permeability curves for the reservoir. So after matching all the experimental data in the lab, so I took the geological data and maps along with the PVT model and the relative permeability curves into the GEM to create the base case model for the reservoir. Then I history match the available primary production data, the pressure and the oil production data. So then the history match model is used to run forecast or to do forecast. So in this case, I just optimize the WAG processes by using Cmos. So with the optimization, I try to maximize the NPV for these processes and also investigate the effect of different parameters, such as the gas cycle time, the number of cycles, the water cycle time, and other parameters to see how can I increase the oil recovery from the reservoir and how can I maximize the NPV for the project. The second case is a field scale model in which I have the data for 7 years of primary production from 1983 to 1990. Also, I have the data for 18 years of the water flooding. So for this case, I just want to optimize the WAG processes for about 27 years. So what I did for this case was a multi-stage history matching. I matched the primary production data as well as the secondary production data. The bottom hole pressures, the cumulative oil production for each well, as well as for entire field was matched from 1983 to 2008. Then I used this history match model to run the optimization for WAG processes. As you can see here, I can increase the NPV for this reservoir from $750 million to $975 million by just optimizing the parameters important for the WAG process, such as slug size, injection pressure, and also the producer operating constraints. So this optimization has done with Cmos. And we came up with a set of the parameters or operating constraints in such a way that we have the maximum NPV for the project. So the physics that I include in this model to do the history matching was equation of state phase behavior that correctly account for the phase behavior of the carbon dioxide and oil. Also, I account for the first contact miscibility and multi-contact miscibility during the injection of the carbon dioxide. It also captures the viscosity variation in the reservoir. The solubility of the carbon dioxide in the aqueous phase was modeled in this model. And also the viscosity and the density of the aqueous phase was changing by the injection of the carbon dioxide. There are some other mechanisms that you can also evaluate their effects on the oil recovery. So the mechanisms such as hysteresis and asphaltene deposition. So in this case, you can see by adding hysteresis into the model, we could see a change in the oil recovery factor that is about 3%. By having the asphaltene precipitation and deposition in the reservoir, you can see a reduction in the oil recovery factor that is about 5%. So therefore, in order to have highest recovery from the reservoir, we should avoid any asphaltene precipitation or deposition in the reservoir. In fact, you need to operate the wells, the injection pressure, or the operating constraint for the production wells in such a way that the asphaltene is not separated from the oil and it's not deposited in the reservoir. So there are some other mechanisms that you can also consider or you can evaluate their effects on the oil recovery factor. So there are some capabilities for the carbon management in GEM. As I mentioned before, GEM is a geochemical equation of state compositional simulator. Therefore, GEM can be used for carbon dioxide storage in saline aquifers. So, And GEM can capture all the mechanisms involved in the carbon dioxide storage. So some of the mechanisms are solubility trapping, residual gas trapping or hydrodynamic, and the carbon dioxide mineralization. So the solubility trapping can be captured with the modeling of the carbon dioxide solubility in the water phase and the change in the properties of the brine. The residual gas trapping or hydrodynamic can be captured with the relative permeability hysteresis. The carbon dioxide mineralization can be captured with the aqueous chemical equilibrium reactions and the mineral dissolution and precipitation kinetics in GEM. In the cases that you have the carbon dioxide leakage from the aquifer, you can couple the reservoir flow with the geomechanics to capture the cap rock integrity or the carbon dioxide leakage due to the change in stress in the reservoir. Based on what I presented today, so CMG can accurately model all the carbon dioxide related processes and all the mechanisms involved in these EOR techniques. So we have WinPerf package that can be used to create a PVT model based on matching all the lab data. So also WinPerf can model the asphalty precipitation, and it can capture all the mechanisms involved in the precipitation and the redissolution of the asphalt. GEM is a multi-phase, multi-component equation of state thermal flow simulator that can be used for the simulation of different processes, such as carbon dioxide flooding, WAG, foam injection, polymer injection, ASP flooding, low salinity water injection, and so many other processes. GEM can also be used for modeling of the combination of the processes, such as low salinity plus miscible injection or low salinity plus ASP injection. So GEM is only commercial simulator that can model the combination of the processes. So we also have the full geochemistry model in GEM that you can capture all the aqueous chemical reactions happening in the aqueous phase or the ion exchange. So we have the geomechanic module that can be modeled for the carbon dioxide leakage or to evaluate the effects of compaction, subsidence, or the induced fracturing in the reservoir. In the other side, we have the Cmos that is a powerful tool to run the sensitivity studies, history matching of the field data, running the optimization for different processes or for different projects, and also doing uncertainty analysis to quantify the uncertainties in the processes and the risk involved in any projects. So I should say that there is no other simulator or simulation package that can do all of these together.
Thank you, Hussein. We will now take up questions. If you have any questions and have not already submitted it, you can do so now using the chat window on your screen. I see there are several questions already here, and I'll try to go over them one by one. The first question is by Jose, and the question is the CO2 injection technology applicable and suitable for heavy crude which has a API of less than 12?
So actually there are a few processes that recently we have seen, especially for the heavy oil, that is the co-injection of the carbon dioxide with the steam into the reservoir, or using the carbon dioxide as an additive into the solvent injection processes. So in fact, the carbon dioxide can be injected as a non-condensable gas into the heavy oil reservoirs, for example, to improve the heat loss in the reservoir, or it can be used as a carrier gas in the solvent injection processes to adjust the saturation pressure of the gas mixture.
The next question is from Kushag Saxena, and the question is, how can we model and visualize asphaltene deposition in 3D using GEM? Is there any keywords that you suggest to use?
So actually in GEM you can have a look on the on the asphalting that is precipitated, flocculated, or the deposited in the porous media in the results 3D. So I think we can send you the keywords for these outputs, but you have the options to make them output, and you see how the asphalting is transported in the reservoir, in which areas it's deposited, and at what temperature and pressure it's precipitated.
And you can also visualize the permeability alteration because of the deposition of asphaltene in
Yes.
3D. The next question is from Dr. Mehran Puladi Darwish, and the question is, are there rule of thumb to suggest when asphaltene deposition should be modeled, that is based on API gravity or SARA analysis along with the reservoir PVT?
For the carbon dioxide injection, actually you should have some experimental data from the lab to see the asphaltene precipitation. For the deposition, actually in some cases we are using the analogy to see what would be the parameters for the deposition. So because if you don't have any experimental data for the precipitation, then we are not sure at which temperature and pressure the asphaltene is separated from the oil. But as long as you are sure about the precipitation, then for the deposition you can use the analogy between or from the experimental data that are currently available in the literature, and you can come up with the parameters for the deposition.
The next question is from Charles Kahn, and the question is, I know foam modeling was implemented in STARS previously. Are you saying that you can model foam in GEM too? Is that a recent development?
Yes, actually from 2014, later we added the empirical model for the foam injection or foam modeling in GEM. So right now you can model the foam injection in GEM, and you can combine it with any other processes like carbon dioxide injection or back processes.
The next question is from Mohammed Reza, and the question is, except for the IFT reduction factor, how do we add the direct compositional effect due to interaction of CO2 and reservoir fluid in relative permeability modeling?
So actually in GEM you can include the effect of the interfacial tension on the relative permeabilities in different ways. One of the methods is to directly define the relative permeability curve as a function of interfacial tension. So in this way, the relative permeability curves are adjusted based on the calculated interfacial tension between the gas and oil. You can also use the endpoint scaling to change the shape or the relative permeability curves as a composition or as a function of a component composition. In that way also you can control the relative permeability curves.
Basically you can define multiple relative permeability curves, and it can interpolate based on the composition of CO2 in a particular grid block. The next question is from William, and the question is, in a case where CO2 storage and oil recovery are the main objective for optimization, is it possible to construct a user-defined multiple objective function in Cmos? Yes, you can define multiple objective functions in Cmos, and Cmos does allow you to define user-defined objective functions. It can be multiple objective functions, and then there could be a global objective function as well. So Cmos is completely customizable in the way you want to define the objective functions. The next question is again from Kushagra Saxena. Can we do rel-from interpolation based on two or more interpolants? Example, salt concentration or IFT or asphaltene precipitation at the same time?
Yes, actually you can do the interpolation, or you can consider the effect of, for example, IFT and hysteresis on the relative permeability curves. Yes, you can.
The next question is from Thomas, and the question is, as mentioned, GEM can handle different processes at the same time, but how to manage uncertainties without smearing them out, process versus process? When you are modeling different types of recovery processes or a combination of recovery processes in a single model, there are various uncertainties associated with each of those processes, and that's where you can perform a sensitivity analysis where you can capture uncertainty associated with different parameters that are related to different processes, and estimate a relative impact of different parameters as well. So again, Cmos comes in handy in order to analyze the results in terms of relative sensitivities of different processes. The other question is from Bob, and the question is how the physical dispersion can affect the oil recovery in conventional CO2-EOR processes.
So actually, as I mentioned before, the molecular diffusion has shown to be a main recovery mechanism in the fracture reservoirs, but still in the conventional carbon dioxide injection processes, we have seen a change in the oil recovery by the addition of the physical dispersions. So for example, if you add the diffusion or the mechanical dispersion into the model, then you will see a change in the oil recovery. That is usually between 5 to 10% of the, for example, original oil recovery.
The next question is from Adrian, and the question is, which thermodynamic model for MCM calculation is more acceptable?
So actually, as I mentioned, in WinProv, we have different options for the multi-contact miscibility calculations. So among these models, the multiple mixing cell and semi-analytical methods are working better. But still, you need to compare different models to see how the MMP is calculated based on the different methods. And it's always suggested to run the slim tube test in GEM, or to just create a 1D model in GEM to verify the calculated the MMP based on different thermodynamic models. In fact, these models are only predictive models, and sometimes they are not predicting the MMP very well.
The next question is from Richard Omake, and the question is it possible to model flocculation kinetics in asphaltene precipitation model?
Yes, actually, as I mentioned, in GEM, you can capture the flocculation mechanism happen during the asphaltene deposition. So the flocculation, there are a few parameters that you will define it, then the GEM will model it and will capture the mechanism involved in the flocculations.
The next question is from Dorji, and the question is it possible to simulate CO2 injection in black oil model with the same certainty as in compositional?
So actually there is, so we call this this type of the modeling as pseudo-miscible method for the injection of the carbon dioxide. Actually, based on the experience, we have seen that some engineers, they just using this method to just run different studies, to just doing the sensitivity analysis and those studies, and they will come up with a final model. So what is suggested is that if you are using the pseudo-miscible model for the carbon dioxide injection, just take one or a few cases from the pseudo-miscible model and then run it under compositional simulation to see that the results is matching or not. Because the main issue is that sometimes during the compositional simulation, we have too much composition variation in the oil because of the pressure or the composition variation. And because of that, maybe you cannot use the pseudo-miscible method for the carbon dioxide injection in the black oil.
The next question is from Jeremy, and the question is there an option in GEM to capture water blocking effects?
Yes, actually, recently we just added a new option in GEM to define the residual oil saturation as a function of water or gas saturation. By using this option, you can indirectly account for the water blocking in the reservoir. So, in fact, you are changing the residual oil saturation, and you are trying to capture the water blocking. This is actually an indirect method.
I see there are still several questions that we could not take just because of sake of time, but we will get back to you individually within the next day. and answer your questions individually. At this time, I'll like to thank Hussein for a wonderful presentation. And at the same time, I hope you've gained a better understanding of some of the complexities and mechanisms associated with CO2 and hybrid EOR processes, and how to use GEM to model these processes. CMG does offer a multitude of training courses for all skill levels. For those of you who are interested in knowing more about CMG's advanced EOR modeling capabilities, there are several courses in our training calendar, and the details of which can be seen on our website at cmgl.ca. We also offer company-specific customized courses on a variety of subjects all around the world. So if you do need to subscribe for a customized course, then do contact us for that, and we will make arrangements for that course. We will post today's recorded presentation on our website within the next 24 hours. You can use your CMGL username and a password to log in and access the material. Also, if you have any questions related to the material presented today, or you'd like to know more about our product offerings, please do not hesitate to contact us by email to sales@cmgl.ca. I'll also remind you that the next webinar is on December 7th, and we'll be talking about advantages of integrating third-party hydraulic fracturing tools in modeling unconventional reservoirs. You will soon get an email for registration, so do register for that webinar, and we look forward to your participation in that. Again, thank you all for joining us today in the webinar on advances in CO2 EOR reservoir modeling.